Hello friends, welcome back to the bench. Our patient today is 2012 to 2014 Toyota Camry ECM. And what's interesting about this is that it is in ECM and TCM in a single package. Very interesting, probably cost saving. Now, the first part is to open it. Unfortunately, it is glued around here with a silicone, so IPA or heating doesn't really do much. What you need to do is use force, no way around it. I figured that the easiest way would be, after removing these screws, screw them on this side so you can screw in some tool to hold it, then this part either in the vise or also use the screws to kind of hold it and just pry it open, just like that. There's gonna be some thermal conductive paste, very sticky, so expect to get a little dirty, after which we get access to half of the board. Now, once we get access to this half of the board, which is relatively useless, there are few components on this side that are prone to damage and can be replaced. However, to access the EEPROM, you need to dig the board out to get to the other side. That's where the interesting stuff is. I started the removal process by wicking those big pins, first applying some leaded solder to reduce the melting temperature, and just wicking all of them relatively clean. This was actually the easiest part of the whole endeavor. The solder melts really well when you apply some leaded solder. You can also do this for all the other pins, just soak them in leaded solder, and the whole process should be a lot easier. Just like this one, you can see how shiny the solder gets when you apply some leaded. Once the pins are relatively clean, what I used is hot air at 380 degrees full blast and a solder sucker. I'm using a slightly better solder sucker than those tiny cheap plastic ones. This one is aluminum and it comes with replacement nozzles, so it soaks in, or it removes the solder a lot more effective than the really cheap ones. But as you can see, it's still not too clean. I can tell over here already that it's gonna give me problems, but it works a lot better than it did with PCI Express port replacement or slot replacement on the motherboards. The pins are relatively big, so they clean off, most of them at least. They clean off, or at least it looks like it's working really well. But there's still plenty of solder on the other side, so the board is still being held pretty well. To actually do it properly, you require a special tool which comes with a tiny compressor and can remove the solder very effectively. However, I do believe that to pull this off, you still need to apply some leaded solder and mix it with this lead-free solder. Otherwise, it's a very difficult process. It definitely takes a lot of patience, and this whole process took me quite a few hours on the span of 2 days. I did about half of it on one day, and the rest of it on another day. As you can see, I only hit the record on the microscope. I didn't want to make a full video out of it because it would be extremely boring if not watched on 8 times speed. Some pins give you more problems, some pins give you less problems, but overall they are all problematic. And it might look, over here it might look like they're all cleaning nicely because we can see through the board, but they're still holding pretty well on the other side, some of them at least. Also mind that the whole device is covered with aluminum, so the entire device heats up really high. It runs really hot. So you can't really touch the device anymore. At this point, the aluminum is so hot that you can't hold it in your hand. So, which works well on one hand because the board is hot. If it keeps the temperature high, it's a lot easier to melt those pins. But in some cases, you will probably notice over here that some of those pins, it looks like I removed the actual pod. So it was heated up too high, and this other sucker unfortunately has a lot of kinetic power, kinetic energy, and is capable of just ripping that pod way off, right off the board. Now, my hope over here is to put the flux on it, heat it up, and the board will just pop out. But that obviously did not happen. After removal, as you can see, it's not the best. But after removal, we have access to both sides. But first, let's look around the back side. So this is the side that we have access to without removing the board. 66101, we have 2 of these. These are fan controller ICs. I'm not sure what exactly do they control. I would have to consult the pinout of the ECM. But we have 2 fan controllers. These are likely the H or half H bridges, and they might control perhaps throttle motor, maybe some airflow control. 6015, these guys, and we have a lot of these. These are N-channel MOSFETs. 6015, dual N-channel MOSFETs. So 2 MOSFETs in each of one of these. So these 2 could create a full H bridge over here. They probably don't, but who knows. They are likely being used instead of little transistors like these. Let's get this right for like turning on the fans and stuff. So instead of using these tiny transistors, those MOSFETs are being used. We can see the gates are over here. This is likely drain or source because we have big pads going in there, and the same here. Going further, what else do we have? 60 what is this one? 6611. Yes, I think so. So that's another fan controller. 6015 dual channel MOSFETs. Now, the Denso chips SF137, SF137. These are obviously available here and there. Proprietary Denso chips. Hard to say what they control over here. I expect some of them control the injectors, some of them control the coils, most likely. And we have two big transistors over here. And so this one is an N-channel power MOSFET. Also, who knows, maybe it controls some fan, some relay, hard to say. And that's pretty much all we have on this side. 836 Denso chip, same deal. And there's one more over here, which is now covered with the thermal conductive paste. Now, as we flip it, let's adjust the focus, and actually let's go even a little higher. There. On the other side, we have a big Denso chip over here. This one reminds me of the chips on Subaru that controls the ignition on the ignition coils. We have two MCUs, this one and this one, in different packages. So one of them controls, or one of them is responsible for engine control, the other one for transmission control. This is most likely in automatic transmission, which doesn't really make much difference. You still have TCM even on manual transmissions. Now, which one is which? Because next to them, this chip is marked with 16H. That is a 2 kilobyte EEPROM. Next to this chip, and next to this chip, we have the same one, 16H, 2 kilobyte EEPROM. Now, the question is, which one holds the VIN? And so, which one is the ECM, which one is the TCM? And I haven't really read them because these chips are 95 series. And my adapter is currently wired for 93C series, which is not a big difference, but the clock is on the different line, and you also have another pin which normally doesn't exist, which is I don't remember, read protect or write protect. Basically, you have one more pin that you need to wire. Other than that, you just need to switch the clock signal from this pin to this pin. But how do we tell whether this one is a ECM or the other one? So this one is removed, so we can inspect the pins. Let's remove this one. I already did that before, and I just held it over here with one pin. There. Just so we can inspect how they connect. So the first pin on this one is here, which means this is input and this is output. You can, those chips use SPI rail, SPI bus to communicate. So you can think of MISO and MOSI as basically input and output. So this is our output. This is the pin we use to read the chip. This pin we use to write to the chip. And as you can see, it's connected to the clock. This is the clock. This is our input. They are connected with a 10K resistor to the chip. So our clock signal goes to our input, which essentially means that this chip is read-only. We cannot write to this chip when our input is bridged with clock signal. Why is that important? Because we do know that you can program your VIN to this ECM using CAN bus, which means this chip, supposedly this chip, if this was the ECM chip, this chip would have to be able to write to the EEPROM. And as we can see over here, this chip is unable to write to the EEPROM. It can only read it. Which means that this one is reversed, so the first pin is over here. So our input is here, and our input goes to the MCU, which means this MCU can write to this EEPROM, which in turn means that this is ECM, and this is what holds our VIN. In turn, this is TCM, and our EEPROM holds, well, whatever the TCM needs to remember. Perhaps configuration, perhaps some measurements, some timing, who knows. I will eventually read those chips. At the moment I don't have the adapter, and I don't want to modify my 93C adapter because I need it for 93C chips. Nevertheless, it's not very complex to convert those adapters. Okay, so that's how we find our VIN. So this will hold our VIN. Now the question is, why would you need to retrieve this chip from over here to read the VIN? Can't you just read it through the CAN, and can't you just program it through the CAN? Yes, you can, but provided that your MCU works. And I have another ECM which is Subaru, but the tuning went wrong, and the operation just kind of stopped in the middle, or there was a communication problem. In any case, the bootloader on the ECM stopped working, which means there's no CAN communication, which is not an issue on Subaru because you just pull the board from the plastic box and just retrieve the chip and maybe just resolder it to the other ECM, or just read it and write it to the other ECM. That's not an issue. But on this one, if your MCU dies for whatever reason, then you need to retrieve this chip. Now, can you just write the new VIN to the new ECM? In most cases, yes. In most cases, that will work. There are cases where there is a configuration written to that EEPROM, and it needs to be copied to the other ECM, the replacement ECM. In which case, if you just program the VIN to the ECM, you get some codes usually related to timing, because that is what usually the EEPROM holds. Some ECMs also utilize the checksum on the VIN, which means you have to know how the checksum is calculated. Otherwise, again, you need to dig out this chip and copy its contents to the replacement ECM. Now, other than that, we have 3 coils over here, which is curious. Again, I don't have a pinout, so I can't really test the voltages over here at the moment. I will eventually, but what we do need is at least one 3.3 rail, which will supply these chips. We also need 5-volt rail that will supply most likely our MOSFETs. They will most likely be driven with a 5-volt or well 3.3 on the gates, and depending on the type, these are N channels, so we need MOSFET drivers. So most likely the drivers are embedded in our MCU. If not, we're probably using something else to drive the MOSFETs, just so we can put higher voltage on the gate. But depending on how they're being used within this circuit. But we're definitely gonna have 3.3 and 5. However, we have 3 coils over here, so I'm curious what the third rail would be. Unfortunately, the board is not marked as we do on Subarus, and each chip has its number, each resistor, each transistor. That is kind of too bad, because it usually helps a lot, especially when you're not sure whether this is a capacitor or a coil or anything else. You see the symbol. If it's L, then you know that's coil. If it's C, you know it's a transistor. So that usually helps, which is too bad on this one, which makes the reverse engineering a little harder. But the board is designed very well. As you can see, it's very neat design. There's plenty of passive components to break. We have a single clock, 4 megahertz clock, which I assume delivers the clock signal to all 3 chips over here. Actually, this one seems to be only dedicated to this chip. Looking at it now. Usually oscillators are close to the chip, like here, right? They're usually very close to the chip. It would not be the best solution to use this quartz over here to create clock signal for this chip. So I would assume that both these chips have internal oscillator, which is typical for MCUs. However, the internal oscillator is usually pretty low. Actually, I'll look at that. 16 megahertz. Here we have tiny quartz for this chip, and here is this 16 as well? Yes, 16 megahertz for this. Okay, so we solved the problem, or we solved the mystery. These packages are kind of difficult to work with, so replacing the TCM MCU would be a hassle. You can do it without the stencil, most likely, unless there's only few connections there, but it's probably the whole chip has connections all across the other side. These are much easier to work with because you don't need the stencil, but it's still relatively difficult to replace these. And that is pretty much it. This is our Toyota Camry 2012, 2013, and 2014. Now, how viable is it to repair these? These are not expensive. To remove the board, well, you need a tool. I shouldn't be doing this without the proper tool, but since it's not a repair, it's just assessment, I just figured who cares. You can see how it melted over here when I was blowing hot air over here to remove it. But to remove this plastic, I don't see any way to remove that. I tried, yeah. But no, this is staying in. So the only way is to desolder these to remove the board. So repairability is really relatively hard, mainly because of that removal process. So considering the cost of it, it's probably not too viable to remove it, to either to replace the or retrieve the EEPROM, or perhaps replace one of these MOSFETs over here. It's probably not too viable economically to perform it on this one, but now we know. Now we know. If you have any problems with your Toyota Camry, let me know. Maybe we can figure something out. But most likely it's easier to just use the CAN bus to program new VIN on the replacement rather than removing this board. That is at least my current assessment. But once I learn a little bit more about this one, as this is the first Toyota I'm working on, then I'll have a lot more to say, and perhaps there's an easier way to remove the board, or maybe something else. Unfortunately, there are no schematics, no board views, and not even the data sheet for the Denso chips, which is pretty common. But as long as you have replacement and you know which chip does what, it's relatively straightforward. You just replace the chip. Alrighty, that'll do, guys. I hope you found this interesting, how Toyota Camry works on the... And actually the most important or the most interesting part is that this is two devices in one, ECM and TCM, which is very curious. It's the first that I see working this way. Thank you guys very much for watching. I appreciate you, and I shall see you in the next one.
If your Subaru Outback doesn't run, number of working injectors is one. Your car shakes like a leaf, and you can't get a relief.